Hi class, this video is on topic B5, springs and conservation of energy. But first let's review what we know from the energy and momentum unit so far. So far we know that mechanical work occurs when some component of a force displaces an object. It's a scalar quantity measured in joules, and it can be positive, negative, or zero, depending on the angle between force and displacement. For a given size force, the most work that can be done is when the force applied is in the exact same direction as the displacement, or in other words, an angle of 0 degrees between those two vectors. For example, a man applying an upwards force to lift this barbell at a constant speed, there is a displacement that's up, and that's the same direction as the applied force. Therefore, the man does positive work on the barbell. The work done by gravity is negative because gravity is down. Another example of negative work in lots of problems is the work done by friction, because friction is opposite to the direction of displacement often. And if we want total work, then we're going to sub in the net force, and it's going to be net force times displacement. Energy is the ability to do work, and we can add energy to a system or remove energy to a system in order to do positive or negative work. Energy is therefore scalar and also units of joules. The work energy theorem states that the total work done on an object is equal to the change in that object's energy. So whatever gain we get in maybe kinetic energy is due to the work that is put into the system. Whatever gain in gravitational potential energy we get is due to the work. There are many forms of energy, such as thermal energy, electrical energy, kinetic energy, nuclear energy, and each type of energy may be associated with motion or energy storage. And we call the stored type of energies potential energy. Examples are chemical potential energy, gravitational potential energy, elastic potential energy. So they all have potential in the name. Total mechanical energy is the sum of the kinetic energies and the potential energies. And this is a very important statement for our conservation of energy problems, which we have already practiced throughout grade 11 and at some points in grade 12. So we have that the total mechanical energy is equal to the sum of kinetic energies plus potential energies. Kinetic energy, which is energy associated with objects in motion, is EK, and it's equal to 1/2 times mass times speed squared. We also might want to calculate the change in the kinetic energy to calculate work, since work is equal to the change in energy. Another type of energy is gravitational potential energy, which is stored energy associated with an object's height above a reference level. We can calculate EG using the formula mass times 9.81 times the height above the reference. It's important to know in grade 12 that we can only use this equation if we are near Earth's surface, where G doesn't vary significantly. So then we can use 9.81 meters per second squared. This quantity, EG, is independent of path. So we only care about the initial and final positions. And what's really important is that you start off these problems where you have a diagram and you establish your reference level. So your height above what reference level is an important question. As a tip, pick the same reference point for different parts of the problem so that you don't have to keep relabeling your diagram. And we also might want to calculate the change or the gain in gravitational potential energy. We also have already covered the law of conservation of energy. The total energy of an isolated system remains constant Energy is neither created nor destroyed. It can be transformed into another type or transferred to a different object. If no work is done in a system, there's no change in total mechanical energy, therefore energy is conserved. So we've got total energy at one point, for example, point A on this roller coaster is equal to the total energy at point B. We sub in what we know is the equation for total mechanical energy. And we always want to start conservation of energy questions with the mathematical statement of the law of conservation of energy, ET equals ET. Once we sub in the next lines, we're really hoping that we can cancel out some of the terms. So for example, at the top of the roller coaster, if it's barely moving, it has no speed, EK is 0 and it's released at the top. And then if it reaches the very bottom, what do we mean by the very bottom? Maybe this is where H is equal to 0 to us based on our reference level that we defined in our diagram. Then we can say EGB is 0, and this simplifies the problem and allows us to solve. We also have gone over the power equation. This is review from last year. That power is the rate at which work is done. Change in energy over change in time is another way to calculate. Since if we do unit analysis, we can see power is also scalar, and it's units of watts. Okay. So now we're moving on to new material. If you're following on along with the student notes package given in class, our slides and examples that we're going to cover here in this video correspond to what used to be called Lesson 5 and Lesson 7. And just due to reorganization of the course resources to fit distance learning, I renumbered, and now we're going to call this topic B5, which is springs and conservation of energy. So you might want to have your student notes package available. You can pause this video and get your student notes package to make sure that you have something, a note to take away for study purposes. So we're going to cover Hooke's law, which gives us a spring force. We're going to cover elastic potential energy, which gives us an elastic potential energy that we can calculate associated with that spring force. Simple harmonic motion, and some conservation of energy problems where we now incorporate that new type of energy that we've learned. By the end of this video, we would want to be able to describe Hooke's law, demonstrate the understanding of the spring constant using equations or graphs, demonstrate understanding of simple harmonic motion and be able to calculate the period of simple harmonic motion. That's what SHM stands for. And that we can apply law of conservation of energy with problems involving this new elastic potential energy. So here we have a spring that's secured to the wall, and we're about to touch the spring. But before any force is applied, the spring naturally rests at what we call an equilibrium position. So the end of the spring we call an equilibrium position, and this dotted line is the equilibrium position for this spring. And we may apply a force to the right to stretch the spring, and we would apply that force and hold it at that displacement. We could apply a force to the left and displace the spring, compressing it. Just think, what do you think? You can pause the video and ask yourself this. What do you think that the red, green, and blue arrows represent? A hint that they're all vectors. Okay, so the red arrows represent the applied forces. So here we have no applied force, a force to the right or a force to the left. The green arrows represent the displacement of the end of the spring as compared to the equilibrium. The blue arrows represent the spring force. So when we pull on the spring, when we stretch the spring applies a force to want to restore back to equilibrium. Same thing when we compress, there is a spring force outwards to try and bring the end of the spring back to equilibrium. So notice that the blue spring force is always in the opposite direction as the green displacement. So that means that the spring always wants to return back to the equilibrium position. And that's why energy is actually stored in this, as we'll see soon. So let's say we want to stretch or compress a spring. We're going to have to apply a force. Let's take a look at the mathematical relationship between how far we want to stretch the spring and the force required to keep it at that stretch position. So we've got the orange spring data and the blue spring data. If we stretch and hold the spring 20, 40, or 60 centimeters, we can see that the force required actually increases, and it increases linearly. So for both of these springs, force and displacement are proportional to each other. The mathematical statement of that relationship is called Hooke's law. It says that the magnitude of the force required to stretch or compress an ideal spring is directly proportional to the displacement of the spring from its equilibrium position. This symbol alpha means proportional to, directly proportional to. So the mathematical statement is spring force is equal to negative spring constant times displacement from the equilibrium. Notice that this is optional, but there was the option to put the vector arrows on F to indicate that it's force vector, not the magnitude of the force. And then we would put the arrow on delta X. That means it's not the magnitude of the displacement, it is a vector quantity. So if we care about direction and make this a vector statement, then we need that negative. And that is just a reminder that the spring force is in opposite direction to the displacement. We can also use this equation, just take the magnitudes of both sides, and then we don't have to use that negative. And of course, when we're doing free body diagrams, where we already take into consideration direction, we do like F to the right minus F to the left. We would not be including this negative there because we're looking at the magnitude of the spring force, maybe being subtracted from some other force. So when we're working with free body diagrams, we're not going to really care about that negative because we're looking at the magnitude of the spring force. The spring constant is this new value that is, it's a measure of the stiffness of the spring. If we look at the units, newtons per meter, that makes sense based on this equation. Notice that the direction, recall that the blue and the green arrows were opposite in direction, so this negative accounts for that. If we compare, if we look back to that FX diagram, the graph for the blue and orange springs, what does the steepness of this line represent? So pause this video and think. Try to answer the question, what does the steepness of this line represent? So to answer that question, let's take a look at about 25 centimeters. So for stretching two different springs 25 centimeters from equilibrium, it takes a lot more force for the blue spring than the orange spring. So the blue spring is more difficult to stretch, and the line of best fit for the blue spring is steeper. A steeper line of best fit means a stiffer spring, and we will get a larger spring constant. If you take a look at what is the meaning of, if I did a line of best fit, created an equation for it, what's the meaning of the slope? If we look at the units, it would be rise over run, so newtons over or divided by meters. Those are the units of spring force, and as you might guess, that is a measure of the stiffness of the spring. So steeper FX graphs are corresponding to springs that are more difficult to stretch or compress. when we say ideal springs, it just means that springs that obey Hooke's law. In reality, there's a region where a spring will obey Hooke's law, which is called the elastic region. Hooke's law, again, is that F and X are directly proportional. So the linear region of the FX graph corresponds to the elastic region where the spring behaves ideal. And then when you go past that, it's the non-elastic region, you're gonna get permanent deformation occurring, and it's not linear between F and X. So now let's try this example. A force of 600 newtons to the right will compress a spring a distance of 50 centimeters. Determine the spring constant of the spring. So we're applying a force 600 newtons to the right. We have our delta x, which is the displacement as compared to equilibrium. Make sure we convert to SI units. There is an assumption that we're holding it there. So the applied force, there's no net force on the end of the spring, and so to get the spring force, it's just the applied force, and we know that F spring equals kx. We can rearrange to solve for K, and we get the force divided by displacement gives us 1200 newtons per meter, and that gives us the spring constant to two significant figures. And going back to our slides and some more examples, if we take a look at some raw data, FX raw data, we could also say which spring was more stiff. So if we take a look at spring 1, if we apply 0.98 newtons force, it does a little bit of stretching. 0.98 newtons force does more stretching for spring 2. So spring 1 is more stiff. So it would be expected to have a higher spring constant. And just to clear up some common confusion, the force is to versus the force is by the spring. So the equation that we just learned, F spring equals negative K delta X, that's the force done, the force by the spring, on, let's say, the person's hand that's trying to stretch or compress that spring. But so this is the force on the hand. The hand is applying a force to the spring, and it's equal to the magnitude but opposite direction. We can just, from problems involving more than one force, we can just look at the magnitudes. It's important to note direction in conceptual problems, but we're often going to get away with just looking at the magnitudes. And if you do consider the vector aspect of this, because they are the same type of force and because they act on two different, they are equal in magnitude and opposite in direction, it is an action-reaction pair. So the F applied and F spring, those are, that's an action-reaction pair. So we talked about the force associated with a spring. Now let's talk about the energy associated with springs, or other ways that we could store elastic energy. So the elastic potential energy depends on the amount of stretching or compressing and on the stiffness of the spring. So the amount of stretching or compressing and the stiffness of the spring. So we've got elastic potential energy in joules is equal to 1/2 times the spring constant in newtons per meter units times the displacement squared. So don't forget about the squared. We could also calculate work by the area under the force displacement graph. Notice it's the area of a triangle, which is how this is derived, if you are interested in that. So let's try another example. We've got a block of mass 0.5 kilograms. It's placed on a level frictionless surface in contact with a spring that has a spring constant of 100 newtons per meter, which has been compressed by 0.3 meters. The spring whose other end is fixed is then released. So first of all, we're going to draw a diagram. We're going to label our givens, determine the total energy of the system. total energy of the system when we are compressed by 0.3 meters. We are compressed by 0.3 meters. That means the object or the spring is 0.3 meters shorter than it would be in its relaxed position. So it's compared to equilibrium. So this is our diagram. And at that point, it's like we've wound up. It's analogous to if we took an object and lifted it up. We lifted it up based on a certain height, we'll be able to calculate EG. So this is, we've compressed it by a certain amount, and based on that amount, we'll be able to calculate energy. So the total energy at that point, since we're holding it in place, it doesn't have any speed, we'll call that H equals 0. The only energy that makes up the total energy is the elastic potential energy, which is 1/2 kx squared. We substitute our numbers in SI units, and we get 4.5 joules. Part B says the maximum speed of the block. If we are storing up that energy, we're gonna slowly take that stored energy and turn it into kinetic energy as it speeds up towards equilibrium. At equilibrium, the object moves away and the spring is not speeding it up any longer. So we're gonna compare position A with position B. So position A is that compression of 30 centimeters, and position B is when the object is at equilibrium, we'll have the maximum speed. So we say total ETA equals ETB, substitute in the answer from part A is equal to 1/2 mv squared, and we isolate for VB, and we substitute in our numbers to get 4.2 meters per second. So note the max speed occurs when the mass is passing by the equilibrium point. At any point in this video, you can pause to try to copy out your own example and then check your answers here, or the PDFs are available on the Google Drive. The last part is we are going to skip the part C because we are going to answer that in a more complicated problem coming up very soon. So simple harmonic motion, as compared to what we've talked about before, you stretched a spring and hold it there, or you were talking about the force required to stretch and hold a spring there, or to compress and hold the spring there. What would happen when a mass that's attached to a spring is stretched or compressed, and then we release that object? So that's what we're talking about here. If we compress the object and then let go, the end of the spring will go back to equilibrium and it will overshoot and stretch, and then it will want to go back to equilibrium, but then it will overshoot and compress. And this repeated compressing and stretching happens at regular time intervals in simple harmonic motion. So amplitude, period, and frequency of these compressions, stretches, these cycles will be constant over time. This type of motion occurs when there's a storing force that's directly proportional to the displacement. And that occurs in this case because maximum compression is when we have maximum force downwards. Maximum stretching is when we have maximum force upwards. And why do we say restoring force? This spring force is constantly trying to bring the object back to equilibrium. So we have an equation to calculate the period, capital T, in simple harmonic motion. And we need to know the mass of the object that is oscillating up and down or back and forth, like right to left. And we need to know the spring constant of the spring. So it depends on what is cycling and also the stiffness of the spring. So if we have these values, then we can calculate period. This is pi 3.14 that we know and love from elementary school geometry. If we take a look at just some diagrams of when we had simple harmonic motion. So maybe we compress this object, then we let it go. As the object is passing by equilibrium, we have maximum speed. Whether the object is going away from equilibrium to the right or to the left, at that moment, there is no elastic potential energy to contribute to the speed. It's just all kinetic energy, so we have maximum speed. And then where do we have zero speed? That would be at maximum compression or stretching. So the object is at equilibrium, we get maximum speed. The object is at maximum compression or stretch is where we get no speed. This would be also where we have the maximum restoring force. The spring force is the greatest here when we have the largest X value, or here, largest X value in the other direction. There is a PHET simulation that I'm going to link to this video below, or that I'm going to place the link to it in the comments below or the description below, and I encourage you to play with that to further understand simple harmonic motion and conservation of energy. Okay, one last example in this, when we're talking about just Hooke's law and elastic energy and simple harmonic motion. So a swimmer with 88 kilograms is standing on a diving board. The diving board has a spring constant that's given, 7,600 newtons per meter. Determine the period and frequency of the board vibrations. So it's important always to draw a diagram at the beginning. So pause your video right now and draw your diagram or write out your givens. So we have an equation that is ready to go. It's ready to sub in our numbers, and the numbers are in SI units already, and we get a period of 0.676 seconds, and rounding that to 2 sig figs would be 0.68 seconds. Now, I think it also does ask for frequency. From last year, I think, so from last year, sound and waves, we know that period, which is the time for one cycling event, is the opposite or the reciprocal of the frequency, so the number of events in 1 unit time. So if we just do the reciprocal of this, we do 1 over this, we get a new equation, or we can just take the number and do 1 divided by our answer for period to get frequency. So we get 1.5 hertz. Okay. So now we're gonna sort of put it all together. Now that we've learned one other type of energy, in addition to EG and EK, we've learned EE. So we're gonna do one conservation of energy problem where we're putting it all together. So how would we do that? So recall the law of conservation of energy, that energy can be transformed but is not created or destroyed. So total energy at one point equals total energy at another. And now we can expand the definition of mechanical total energy, because we have another form of potential. So we've got potential from height, and we've got potential from the stored, like the spring or the rubber band. So EK plus EG plus EE is equal to ET. So if we have this car at some height and we release it, and it hits this spring. This is a toy car, by the way. When we get to the example, it's only 5 kilograms. So that toy car has gravitational potential. As it falls down this ramp, just like a grade 11 problem, the EG level is going down, the EK level is going up. Whatever we gain in EK by the bottom was equal to the EG at the top. And then that EK is going to go into EE. So EK lowers, or speed lowers, as the object is compressed. So let's do a problem like this using our new equation for elastic potential energy. So a model car of mass 5, this is like a toy car, 5 kilograms, slides down a frictionless ramp into a spring with a spring constant of 4,900 newtons per meter. If maximum compression of the spring is 22 centimeters, determine the height at which the car was released. A question like this, you kind of have a sense this is like a roller coaster problem, a spring equivalent of a roller coaster problem. It is beneficial to read the entire problem and highlight all your givens before you get started. Part B is calculate the speed of the model car when the spring has begun to compress by 15 centimeters, and then determine the maximum acceleration of the car after it hits the spring. So let's take a look at writing up a solution together. This is a good time to pause and check to see what diagrams you would draw before you see my diagrams. And then resume the video when you feel like you've given it a good shot to try diagrams for all the different parts. Let's do together example 1 from the Springs and Conservation of Energy pages of your student notes package. Let's always read the question first and then draw a diagram. So we have a model car of mass 5 kilograms that slides down a frictionless ramp into a spring with a spring constant that's given of 4.9 kilonewtons per meter. So let's write down any important information. We have mass, and we have the spring constant given. That is 4.9 kilonewtons per meter. And there's a diagram given. And it says if maximum compression of the spring is 22 centimeters, determine the height at which the car was released. And then calculate the speed of the model car when the spring has been completely compressed by 15 centimeters. And then determine the maximum acceleration of the car after it hits the spring. So it would be beneficial in this question to think about all the parts and the conservation of energy, the transformations of energy that are happening. So what transformations are happening? At first, the car is at the top and we release it from the top. So we just have gravitational potential energy. That car is going to roll down the ramp past the equilibrium point of the spring. That would be the length of the spring without any force. The end of that length is called the equilibrium point. Once the car rolls down the ramp, it's going to go past that equilibrium point and compress the spring. From point A to the equilibrium point, we've got gravitational potential energy turning into kinetic energy, just like in grade 11 problems or problems that you saw from lesson 3. But instead of all that gravitational potential energy converting to kinetic, it's actually all going to convert to elastic potential at the maximum compression. At the maximum compression, there is no speed. So that is key. Highlighting maximum compression, and that phrase will mean that the speed of object B is 0 at that point. Its speed is 0. That's why it's the maximum compression. It would keep going if it did still have some forward speed to the left. So maximum compression means VB is equal to 0. We have enough in these 2 diagrams to write our conservation of energy statement that's going to help us solve for problem A. So for problem A, we're looking for the height at which it was released. So remembering that whenever we're talking about potential energies, you have to have a frame of reference. If you're talking about elastic potential energy, you need to know the starting reference is equilibrium, and that delta X is measured compared to that. With the other form of potential energy in this problem, gravitational potential energy, you need to know height above what reference. So it makes sense in this problem for all parts of the question and all of these diagrams to say that the level of the spring is height equals 0. And therefore, what we're looking for is this height here for part A. We're looking at the height at point A of the object. Okay, so starting part A, we want to start with the law of conservation of energy. The total energy at A, the total mechanical energy at A is equal to the total mechanical energy at, we've got these different points, these different diagrams. So does the second diagram here give us enough comparison with this first diagram to solve for the height at A? Well, let's just take a look at, if we write this statement, do we have enough to solve? total energy at any point is made up of the sum of the potential types of energy and the sum of the kinetic types of energy. So in this case, it's EGA plus EKA plus EEA equals EGB plus EKB plus EEB. So that's the sum of the gravitational potential, kinetic, and elastic potential for each side. And we always start with that, but we really hope that we can simplify. We can simplify this a lot. At point A, there is no spring, there is no elastic potential energy. There is also no speed because it says we're going to release it from that height. So there's no kinetic energy. So the only form of energy is gravitational potential at point A. On the left side of this equation, it simplifies to mgh. So we've got mgha. We're not going to bother to put a subscript for m because the mass of this toy car doesn't change. So what does that equal? If we look at the types of mechanical energy that exist at B, as A was sliding down, EG was turning into EK. At the equilibrium point, this was the maximum speed. So there was maximum kinetic energy, and there was no elastic energy because you haven't started to compress the spring. But as you compress the spring to 22 centimeters, because it's the maximum compression, we don't have, speed is 0. So we don't have any kinetic energy. We definitely have elastic potential energy. And because we set H equal to be 0 at the level of the spring, we can cross out gravitational potential energy as well. So this whole line simplifies to EGA equals EEB. We've learned that elastic potential energy is 1/2 K delta X squared, and delta X is specifically the delta X at A, which is maximum compression, in order for us to have made that, to simplify in that way. And then to solve this, we want to find HA, so we simply move everything to the other side. 1/2 K delta XA squared divided by mg. Substituting in our values in SI units. Kilonewtons per meter is not SI units, so we have to turn it into newtons per meter, times 22 centimeters is also not SI units, so we have to turn that into meters, divided by 5 kilograms times 9.81 meters per second squared. And for our height, we get 2.4175 meters at A, and rounding to 2 significant figures would be 2.4 meters. We did use 9.81, and that is a measured number. We did chop it off at 3 significant figures, but our delta X and K values were given to 2 significant figures, so that we limit it to 2 significant figures. So all we needed for part A was the first 2 diagrams, comparing point A with point B. For part B of the question, it's asking for calculating the speed when the spring has been compressed by 15 centimeters. So if you would think that the third diagram happens after the second, we compress to point B, where all the EK has been used up for EE. We've gained EE as much as the EG we had at the beginning, or the EK we had at equilibrium. All of that energy is now EE at point B. Now, the car is going to move outwards, and it's only a 15 centimeter compression. What is the speed at that point? It actually doesn't matter if you're thinking of it as the speed at 15 centimeter compression that happened before or after. So in other words, it doesn't really matter if you're solving for that speed or that speed. it would be the same. I think for me, it makes the most sense, especially the way I drew those diagrams, to think of it as the speed that's going to the right at that point. So for part B, I want you to pause and think, what total conservation of energy statement is going to be helpful in solving for the speed at point at this point. So hopefully you realize that we need total energy at C to be one of the terms. What does the total energy of C equal? It equals the total energy at B. It equals the total energy at A, but which is the most useful? The most useful that I'm going to choose is the total energy at A because it's simplified to just mgh. So for part B, I'm going to start with total conservation of energy. The total energy at A equals the total energy at C. C, total energy, has the speed that I'm trying to solve for embedded in it, and ETA is known, and it's simple, mgh. We substitute in mgha for total energy at A for the same reason in part A. And then for total energy at C, what forms of energy are involved at part C? We have both kinetic energy and elastic energy. Speed is not zero and compression is not zero. The only thing that is zero is our height is equal to zero because of the reference that we've selected. So 1/2 mass V at C squared plus 1/2 K delta X squared is going to be our statement. And we are trying to solve for V at point C. Do we have everything else? We have mass, gravity, height at A. Now, this is a calculated value, so we want to make sure that we don't use the rounded value. We want to carry forward the unrounded value. We have mass, we have spring constant, and we have compression at point C. So we have everything else except for VC, and we can solve for that. You want to question whether we can cancel out masses, or maybe can we cancel out the halves? We cannot cancel out the masses because it doesn't exist in all terms, and we can't cancel out the 1/2 because it doesn't exist in in all terms. So we have to rearrange from there. So isolating VC, we have our equation, we're ready to sub in numbers. You might be tempted to cancel out the masses, but again, we can't do that because it's not in all terms. So VC is equal to the square root of 5 kilograms times 9.81 meters per second squared times the height at A. We solved for that number. Make sure you're using the unrounded number. Make sure you're using SI units. Make sure you check your units that they will cancel out. And don't forget the squared, x squared. I always forget that. And it's the square root of the entire thing. For your final speed for this part, you get 5.0 meters per second squared. The last part of this is asking for the maximum acceleration of the car after it hits the spring. The maximum acceleration of the car. So solving for acceleration, we're going to go back to our kinematic equations. You know, VI, VF, A, delta T, delta D. which of these things do we have? If we're talking about maximum acceleration, we're talking about where an initial velocity is 0, where we're at maximum compression. So that's when the box is at point capital B. The final velocity is when we're going the fastest. That would be at point D. So I have a little diagram for realizing where would be the maximum speed. It would be when the object is at equilibrium, because there wouldn't be any elastic potential there, because there's no compression compared to equilibrium, and there's no gravitational potential because of the reference level I chose. So I don't actually know my speed at D, but let's see if we know enough from the others that we could solve. Do we know acceleration? This is actually the key thing that we're solving for. We don't know time. Displacement. Do we know displacement? From B to D, that would be delta X, which is 22 centimeters, because we're comparing maximum compression to point D, which is equilibrium. So this is really delta X at B. So our steps here, our first step is to solve for VF, which is the point D. And then our second step is going to be solving for A, our maximum acceleration. So in step 1, we're going to compare 2 points. Obviously, you have to use ETD as one of the 2 terms, but you can choose between A, B, and C for the other side. ETA is the simplest because we already know that's mgHa, and then ETD is its only kinetic energy, so it's 1/2 mvd squared. In this case, our masses cancel out, and solving for Vd is the square root of 2gHa. So from gravitational potential to kinetic, before it touches the spring, this is a piece that we have done. This piece of this longer problem is what we have done in grade 11 and in lesson 3. So your speed is 6. Actually, there's no need to round it. There's no point in rounding it, because I'm just going to carry this number forward into step 2, and I don't want to accidentally use the rounded number anyways. Vf squared equals Vi squared plus 2a delta d is what's going to connect what I'm looking for, acceleration, with the things that I now have, the 3 things that I now have. So acceleration is Vf squared minus Vi squared divided by 2 times delta d. My Vf, I'm going to use my answer button or a stored value, squared minus 0 squared divided by 2 times 0.22 meters. I almost accidentally used 15 centimeters here. So that's why it's really important that I have a really nice label diagram and I use my subscripts throughout. And for acceleration, you would get 110 meters per second squared, and it could be considered acceleration when the object is going, when the car is going from the max compression from B to D, or it could be considered deceleration. So you're really solving 2 problems by getting that number. I encourage you to go back to the series of diagrams that I hope you've drawn to solve this, and see if you can rehearse what are the energy transformations at each point, because this is a problem where there's a lot of variations of it, and I could ask a lot of different things from this base question. Okay, so that was our big challenging problem that brought together a whole bunch of stuff from this chapter. When you're faced with a long problem-solving question, make sure you're going back to the GRASS method where you're identifying the givens, identify what's required, do analysis to see if you can connect what you have with what you need, draw a diagram, write your references. So be very clear and practice these a lot. So speaking of practice, you have these practice questions to reinforce all that was in this video. And don't forget to submit these practice questions to the Google Classroom task, as well as there is a very short trivial exit ticket question just to see if you got to the end of this video. Thanks for watching.